Good day. This is Agape Mamphasa, student number 181058883, and this is my presentation of a buffer overflow. So, what is a buffer overflow? According to the NIST IR 7298 glossary of key information terms, a buffer overflow is a condition at an interface under which more input can be placed into a buffer or data holding area than the capacity allocated, overwriting other information. Attackers exploit such a condition to crash a system or to insert specially crafted code that allows them to gain control of the system. So the analogy that Dr. Dlamini used in class is simply picturing a bucket, and that bucket is being filled with water to a certain extent to which the bucket can no longer hold the water. So that is a buffer overflow. So with regards to my demonstration here, I'll be using an integer overflow. An integer overflow happens when an arithmetic operation attempts to create or store a value outside the range that can be represented with a given number of digits. The result can crash the program or give you the wrong result. So essentially the implementation depends on the programming language, and it all starts with registers. Registers are the smallest units of computer memory. As such, different registers have different constraints. For example, a 4-bit register can represent 15 values, an 8-bit register can represent 255 values, a 32-bit register can represent 65,535 values, and a 64-bit register can represent 2 to the power of 64 minus 1, which is 4 billion values. So these limitations in the registers are carried over to the programming languages and their capacity to represent certain numbers outside certain ranges. So for my demonstration, I'll be using Java. Java has 4 integer types: bytes, which use 8 bits, shorts, which use 16 bits, ints, which use 32 bits, longs, which use 64 bits. With this demonstration, I'll be using the int and long data types. And with regards to overflows in Java, to increase reliability, the language simply wraps around an overflow rather than crash the program. This is not critical to the system, but affects the reliability of the results. For example, in a financial application, if an individual's wealth exceeds 2,147,483,647 rands, and that individual gets 1 rand richer, because we've reached how much an integer can hold, which is 32 bits, can hold, an overflow happen, and all of a sudden the individual is 2,147,483 147,483,648 rands in debt. So as you can see, the severity of a buffer overflow. So the problem that I'm going to demonstrate is the year 2038 problem. So it's been projected that calculated that by the year 2038, the 19th of January at 3 a.m. in the morning, 14 minutes and 8 seconds, all systems that are holding the value 2147483647 will experience a buffer overflow. Now, as you can see, this value 2147483647 is equivalent to the time 2038-01 19th at 3 a.m. in the morning, 14 minutes and 7 seconds. So as soon as the clock reaches 8 seconds, all systems that are holding or calculating this value will experience a buffer overflow. Let me demonstrate. So let me just compile my Java program and let me just run it. So as you can see, this is the time before the 8-second mark. So as you can see, it's normal. We can reconvert this value back into Unix time. But as soon as the value, the time reaches the 8-second mark, we get a negative value. So an 8-second mark is reached when we add 1 to the current Unix time. And as soon as we reach the 8-second mark, we get a negative value. Thus, if a clock or a program tries to reconvert this value back into its equivalent unit time, it's gonna have a hard time reconverting it because there's no such thing as negative time. So hence why the severity of these types of overflows can have to any system or running application.